I'm now going to try and work through all the problems that were on the practice test. I just call this the final exam review problems. So here, as long as there's enough room, I'll try and do my work here near the questions. And I'll say a couple things before we begin. A lot of times on these exams, especially some of these exams where there may be multiple choice questions, you know, there's always usually more than a couple ways to solve a math problem. So typically what I do for myself is I try and determine what I think is the most straightforward, easy to understand way. So that's what I'm going to do. So it may not always match up with what the book might say, or even if you look at how my math lab would solve this problem. I do have the answer key, so as I work through these, I'm going to check my answers. Hopefully, I don't make too many mistakes. If I happen to make a mistake, I'll try and quickly correct it and see if I can see what I did wrong. But of course, the way math is, we all are going to make mistakes, but I will try and keep it to a minimum. So here's the first problem. Find the vertex and axis of symmetry of the quadratic function. Determine whether the graph is concave up or concave down. Graph the quadratic function. So we've got a quadratic function. When you graph a quadratic function, it's going to be a parabola. If it opens up, this is concave up. This is concave down. This equation is in a certain form, and some people like to use the equation in this form. What I prefer to do is just go ahead and multiply out the parentheses and use it in the form, sort of like the standard quadratic equation. So I'm going to put my equation in this form, and then I'm going to answer all these questions. That's just the way I prefer. So really what I've got to do, I've got to FOIL x minus 3 squared. Now, I'm going to do that in my head, and hopefully won't make any mistakes. I believe it should be x squared minus 6x plus 9. So what I'm going to do now is I'll distribute the -2 to everything inside the parenthesis, and then add this 5. So therefore, my equation is going to be -2x squared. -2 times -6x is plus 12x. Then -2 times 9, that's going to be -18 plus 5. So I believe it should be -13. Now, when I have the equation in this form, I can figure out some things. First of all, concave up and concave down depends upon the value, the sign, actually the sign of A. So A is the coefficient in front of the squared term. If A is positive, then it's concave up. If A is negative, it's concave down. The way I remember this is a positive person smiles. This looks like a smile. Negative person frowns. You can see here, A is -2, and because it's negative right away, I can go way down here and say the graph is concave down. Now, parts A and B, they ask for the vertex and the axis of symmetry. When you find the vertex, you basically also found the axis of symmetry. So let's go find the vertex, and then we'll almost be done. So when your equation's in this form, so let me define the vertex as 8 sub v, that's a v, and y sub v. And there's a little formula that we can always use to find the vertex if our equation is in its standard form. And the little formula is the x of the vertex is negative b over 2a. So if you want to use this on the exam, you've got to memorize this little formula. So negative b is 12. 2 times a, and a is minus 2. So this is negative 12 over negative 4, which is a positive 3. So right now, I've just determined the x of the vertex is positive 3. How do I find the y of the vertex? Well, I can go back and just plug in x into my equation. I can even plug it into this equation. These are the same. And g of x, in a sense, is going to be my y. So if I plug in, this one's pretty simple. If I plug in 3 in for x, 3 minus 3 is 0 squared. This whole thing ends up equaling 5. So I know the vertex is 3, 5. So once again, you can always, if the equation is in this sort of standard quadratic form, you can always find the x of the vertex with this little formula. Once you find the x of the vertex, you can plug x back into the original equation, and that gives you the y of the vertex. So I can go ahead and plot that point here. This is a pretty small graph, but 3, I guess each tick mark, 1, 2, 3, 4, 1, 2, 3, 5. That's the vertex. Now, since I know this is a concave down, it's going to go like this. So I know the axis of symmetry always splits the parabola right in half. So I'm not going to draw this in here yet because I need to find a couple more points. But I know my axis of symmetry is going to cut it right in half. So it's going to be x equals 3. And the axis of symmetry is always the same as the x of your vertex. So I've really answered all the questions. All I need to do is graph this. So this is my vertex. What I don't know is sort of how wide this parabola is. So what I'm going to do is I'm going to actually take and plug in a couple of values for x. Matter of fact, just to sort of make it simple, what happens when x is 0? If I go here, when x is 0, y is minus 13. So I'm way down here. It's going to be a pretty skinny parabola. Let's choose one more point. How about when x is 4? Maybe I'll go up here and use this one. So when I put in a 4, you get 1 squared times minus 2 plus 5. I believe it should be 3. So of course, within my math lab, you have to know how to graph things, but it should look something like this. Pretty skinny or narrow parabola. All right, so that's problem 1. Let's see what's next. Problem 2. It's like another quadratic equation. Of course, this one, they give it to us in what I call the standard form. So they want us graph the quadratic equation. Does it open up or open down? That means it's concave up or down, axis symmetry. All right, let's just go through all these and take them as they come. So let's, it says graphing, let's save the graphing after we figure all this stuff out. After we figure this stuff out, then the graphing should be pretty easy. First of all, does it open up or down? Well, here, what is A here? A is whatever, A is the coefficient for the x squared term. So A is going to be 1, and it's a positive number. Like I showed you here, when A is positive, it opens up, it's concave up. So it's going to be this. What are the coordinates of the vertex? Well, it's the same as the problem we just did. If I use our little formula, x of the vertex is negative b over 2a. Negative, now b is a negative 2, so it's a negative 2 over 2a, which is 2 times 1. 2 negatives make a positive, so it's 2 over 2. Looks like the x of the vertex is 1. Now I simply have to plug 1 in for x, and that'll give me y. So this will be 1 squared, which is 1, minus 2 times 1, which is minus 2, minus 3, minus 5 plus 1, looks like negative 4. Matter of fact, if I want to, I can go ahead and plot that. So the vertex is 1, negative 4, and it's going to open up. So it's going to eventually look like that. Axis of symmetry, once again, it's going to be the same as the x of the vertex. It's going to split this parabola right in half. So it's x equals 1. Now here's something a little different. They ask about x and y intercepts. Sorry, x and y intercepts. So the way you find intercepts is for x-intercept, set y equal to 0 and solve. I'm not going to take the time to teach about this, but this is how you find the x-intercept. So you take your equation and you set x equal to 0. So my equation, I'm going to replace f of x with y. So I set y equal to 0. And I need to solve this equation. And whatever my solutions are, those are going to be my x-intercepts. This is a quadratic. Thankfully, I think it factors. So I can solve this pretty quickly. I think the factors are -3 and +1. Because if you multiply them, you get -3. If you add them, you get -2. Therefore, my solutions are going to be x equals 3 and -1. I can go ahead and say that those are actually my x-intercepts. So I have -1 and 3. So here, I actually have 2 x-intercepts. And if I want to, I can graph those. So those are where it crosses the x-axis. So -1 and 3. So even now it gives me an idea of what this parabola looks like. Now next it asks for the y-intercept. Well, the y-intercept, you do the opposite of the x-intercept. For the x-intercept, you set y equal to 0. For the y-intercept, you set x equal to 0 and solve. So here's my original equation. This is pretty simple. If x is 0, this is 0, this is 0. You end up with a y-intercept equaling -3. And I can go and plot that. So that says that the graph is going to cross the y-axis at -3. So let me just go and graph this because the last few questions are about domain and range. And once we can see the graph, the domain and range are pretty simple. So it looks like this will go something like this. So down here, let me just show you the question, domain and range. Domain is the value of x. You look at the graph, how far, well, first of all, as an interval, we look at the smallest value of x. So how far to the left, how far in the negative x direction does this graph go? Well, parabola, it continues to get wider and wider. So you can imagine that the smallest value, the smallest x value of this parabola is -infinity. And the largest x value is +infinity. So therefore, we say the domain is going to be -infinity to infinity. Now the range is the values of y, so range is up and down. So in interval, you start with the smallest value. How far down? What's the smallest value for y where this graph exists? Well, down in here, there's no graph. The graph starts when y is -4. So therefore, my range is going to start at -4, and then it's going to go to +infinity. So I do a bracket here because -4 is part of the graph. So it actually starts at -4 and it goes to infinity. Now the last question is, determine where the function is increasing or where it is decreasing. So the idea is as you move from left to right, if it goes down, that's decreasing. If it goes up, it's increasing. So as I trace out this graph from left to right, it's going down, 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 down until I get to here. And this vertex is where it changes. The vertex is when x is 1. And then this thing is increasing. So the left half of this graph is where it's decreasing and the right half is increasing. And it looks like x = 1 is where it changes. So increasing is the right half. So increasing starts at 1 and goes to infinity. And then decreasing. Now I'm looking at the key here, and this is just where there might be a problem of definitions because in the key, they want to put a bracket here, which means you include the value of 1. Now, what I was always taught, since 1 is the vertex at 1, that's when this graph is sort of like perfectly, it's right in between decreasing and increasing. I was always taught you don't include that transition point. Now, the good thing is on the exam, if you have a problem like this and you would happen to put a parenthesis here and it would be counted wrong, when I go in and check for partial credit, I would go ahead and give you credit for that because I'm not sure. I think that's sort of a judgment call. It's not cut and dried. All right, so that's another problem where we're looking at quadratic equations. Let's see what is next. Number 3. Let me go ahead. Solve the following inequality. All right, let me just do this the way I do it. I'll just talk as I go. Once again, I'm not really doing a full teaching of this. I'm just working through these. First thing you're going to do is get everything on one side. So I got to subtract 2 from both sides. So this equation is going to become x squared plus x minus 2 greater than or equal to 0. Now, in order to do these problems, this thing really has to factor. Doesn't always, but it makes it a lot easier. And this problem does, in fact, factor. Factors would be +2 and -1. Because when you do this, then because of factors, we can find the zeros of x, and the zeros are the values of x that cause this expression equals 0. Another word for these are x-intercepts. If we were to solve this equation, set equal to 0, it's the solutions. It's all the kinds of things we've done before. So what we call the zeros of x are -2 and 1. It's whatever causes these parentheses to be 0. So what I do, once I have my zeros, I make a little graph here. Here's -2, and here's 1. And the zeros sort of break my graph from our chart up into regions. So I end up with 3 regions. And then what I do is, well, the whole point is now, these regions, this expression in these 3 regions, each of these regions is going to always be positive or negative. I don't know what it is, but region 1, I have to see if that's a positive or negative region. Region 2, the same, region 3. So the way I do it is what we call a Sine Chart. TP stands for test point. In region 1, I want to choose a value of x in region 1. I'll choose -3. Region 2, I need a value of x between -2 and 1. I'll choose 0. Region 3, I'll choose a value of x in region 3. I'll choose 2. And then this OV stands for overall. In each of these regions, I'm going to use this test point to determine whether that region is a positive or negative region. And when the way you do it is, you take your test point and you go back here and you plug -3 in for x. And I don't really care about the number, I care about the sign. So when I plug in -3 for x, -3 plus 2 is -1. This first parenthesis is negative. When I plug in -3 for x here, -3 minus 1 is -4. Both these parentheses are negative, and because we're multiplying these parentheses, 2 negatives make a positive. I've just now determined that region 1 is a positive region. That means if I choose a value of x in region 1, in other words, if x is between -infinity and -2, that is always going to cause this expression to be a positive number. Let's see what happens in region 2. My test point is 0. I plug in 0 into region 2. This first parenthesis is now positive. I plug 0 into this parenthesis and it's negative. A positive times a negative. Region 2 is a negative region. That means if I choose a value for x between -2 and 1, and I plug that value into this expression will always be a negative answer. So region 3, I'm going to use a test point of 2. I plug 2 in here, it's positive. I plug 2 in here, it's also positive. You multiply 2 positives, you get a positive. Region 3 is positive. So once I've done this, now I go back to my original problem. I want to find the values of x that cause this expression to be greater than or equal to 0, which means I'm looking for the values of x where it's positive or 0. Well, here are my two regions. These are the positive regions. So I have to union these together as an interval. So the interval for this, for region 1, is going to be negative infinity to negative 2. Now at this negative 2 is where this expression is 0. And since I'm including 0, I put a bracket. And then this region 3 starts at 1 and it goes to infinity. So that should be your answer for number 3, solving a quadratic inequality. Okay, here's another one. Here, everything's already on one side. Now this doesn't factor, but I still have to, in a sense, solve this. What I'm really doing is to find the zeros. I take that quadratic expression, I set it equal to 0, and I solve for this. Since this doesn't factor, my only option is to use the quadratic equation, right? Quadratic equation says negative b plus or minus square root of b squared minus 4ac over 2a. I think if you need this, this is on the formula sheet for the exam. So a negative b, and b is negative 2, so negative negative 2 plus or minus b squared, negative 2 squared is 4, minus 4 times a is 1, so 4 times 1 is 4, times c, 4 times 7, which is 28, over 2a, 2 times 1. Now right away, I see a problem here. And the problem is, if I look under the square root, 4 minus 28, I'm going to have the square root of negative 24. And since they're asking, it's assuming they're looking for real solutions, real numbers. We do not have a real number here. The square root of a negative number makes it a complex number. So if I look at my answers here, I can either give a solution or say there's no real solution. As it turns out, for this one, there's no real solution. So there's nothing else to be done. All right, number 5. Last one on this page. Solve the inequality f of x greater than or equal to 0. So they give you the equation, but the point is they actually graph it for you. So if they give you the graph, this is a pretty easy problem. Because all we're doing is we're seeing where is the function, in this case, greater than or equal to 0. The function is like y. You can think of the function as being like the x-axis. So anytime this graph is anytime y is a positive number, that's a positive function. Down here, when y is negative, that means the function is negative. So I just have to figure out where on this graph is it above the x-axis. That's where the function's positive, and that's what I'm looking for. So you can see it's positive here, looks like until you get to negative 2. So this is my first interval, negative infinity to negative 2. And so once again, since I include 0, the function is 0 at -2, I go ahead and put a bracket around -2. And then I've got another positive piece right here. And I'm guessing this starts at 3. So I would say then starting again at 3 and going to infinity. So if I look at the answer, that is actually correct. So they give you the graph. It's not a very hard problem. All right, let's see what's next. All right, number 6, use rational zeros theorem to find all real zeros upon a function. So thankfully, sometimes these problems can be pretty difficult, but this one actually factors, and a factor is what we call factor by grouping. Hopefully you remember that. So factor by grouping says you break these up into 2 groups of 2 and you try and factor, and then you try and factor these 2 separately. And then after you do that, you can make some progress. So 3x cubed minus x squared. The GCF of those 2 terms would be x squared. So I factor out an x squared. I have 3x minus 1. So that's factoring the first 2 terms. And then 3x minus 1, actually I can't factor it. So I just am going to write 3x minus 1. But I'm going to put it in parentheses, so hopefully you can see I've actually got identical parentheses here. So what you can do is I can sort of factor out the whole parenthesis. So this parenthesis times x squared plus 1. So if I'm looking for the zeros, I'm basically going to set that equal to 0 and solve it. So what you do is you take each of these parentheses and you set it equal to 0. So the first parenthesis, 3x minus 1, if I solve this, so x is 1/3 is going to be a solution or a 0. Now I've got to take the second parenthesis and solve this. But you end up with, and once again, it's not going to be a real solution. So the only solution, actually, the only 0 is 1/3. And down here, they actually ask you, after you factor it, they sort of want you to rewrite this equation. So I would say 3x minus 1 Now, what's interesting is I look at the answer and I'm not quite sure. I mean, I have the same thing. What they did, they took this first parenthesis and factored out a 3. I don't know why. So it ends up being once again, if you have this on the test, you get credit for it. I'm not sure why they wrote it this way. Anyways, so that's number 6. See what the next one's about. Oh, looks like the same thing. Find the real solutions Find equation. So we're going to do the same thing. We have 4 terms. Going to try to factor by grouping. These first 2 terms, I can factor out a x squared. So I have 2x minus 3. And then these next 2, I can factor out a 5. I'm going to factor out minus 5, and you'll see why in a minute. So inside the parentheses, if I factor out a minus 5, I have 2x minus 3. Now, once again, here are 2 identical parentheses. So I can factor out the whole parenthesis, and you get x squared minus 5. So now I take each of these parentheses, set it equal to 0. So this one's going to give me a solution of 3/2. Now the second parenthesis, so if x squared equals 5, if I want to solve this thing, what do? Take the square root of both sides. So you have x equals plus or minus square root of 5. So those are also zeros or solutions. And I think in my math lab, they probably want you to write those separately. So you would put negative square root of 5 and then square root of 5. All right, number 8. All right, composite functions. So this is something, the way I do it, at least for me, makes it not too difficult. So here we've got 2 functions, f of x and g of x, and they ask for 4 different compositions. So let me show you how I do composite functions. Let me go up here to the top. The first one is f composite g when x equals 4. So here's how I write composite functions, which makes it, for me, a very simple problem. A composite function is basically what we're doing is f of g of 4. So a composite function, another way of saying that is f of g of 4. What that means is I'm going to first go find g of 4. I'm going to go to my g function, plug in 4 for x, get a number, and then I'm going to plug that number in for here, and then we'll see what we do next. So g of 4, if I plug in 4, and for this g of x, I'm going to have 4 minus 1/2, 4 squared, which is 16. So 16 times 1/2 is -8. 4 minus 8 looks like, oops. Yeah, g of 4 is -4. So that means now, since g of 4 is -4, I put in -4 for g of 4, and now I need to go figure out f of -4. So I go to my f function, and I plug in -4 for x. So 3x squared, -4 squared is 16. 3 times 16, I believe, is 48 minus 2. If I had to make any math errors, this is 46. So we'll do the rest of these, but the key is I always rewrite my composite functions in more pure function notation. So for instance, G composite f of 2 before I do anything, I rewrite this as G of f of 2. So what that says is, let me go find f of 2, which means I go to the f function and I plug in 2. So if I plug in 2 to the f function, let me do it up here. 2 squared is 4, 4 times 3 is 12. Looks like 10. If f of 2 is 10, and that goes in here. So I'm really looking for is g of 10. Now I go to my g function. If I plug in 10, it's going to be 4 minus 10 squared is 100. Half of 100 is 50. Looks like minus 46. All right, so hopefully you're getting the hang of this. These composite problems are not too hard. At least I don't think they're too bad. So here's f composite f of 1. So f composite f of 1, I rewrite it f of 1. So let's go first figure out this inside here. F of 1 says you go to the F equation and plug in 1 for x. It's going to be 3 minus 2. It's going to be 1. If f of 1 is 1, I plug in 1 for f of 1, and then I have to go find f of 1. Well, f of 1 is still going to be 1. So f composite f of 1 is 1. Now, last one, G composite G of 0. I rewrite as G of 0. So G of 0, go to my G function, plug in 0 for x. It's going to be 4 minus 0. So G of 0 is 4. So now I plug in 4 for G of 0, and now I need to go find G of 4. So go back to my G function, I plug in 4. So that's going to be 16. 4 minus 1/2 times 16, 1/2 times 16, 8. 4 minus 8. I didn't confuse myself. I believe the answer is minus 4. All right. Hopefully not too bad. I think the next one, we have another composite function. Although this one, they're not looking for a numerical answer, but they're wanting us just to give the expression. So for number 9, f of x is 7x plus 3, g of x is x squared. Find the following composite functions and state the domain of each. So let's figure out, we'll do the composite function first, then we'll talk about how to determine the domain. So the first one's f composite g, and you do the same thing I just did. F composite g, I rewrite as f of g. That means you go to your f function, and every place you have an x, you plug in the g function. When my g function is x squared, my f function is 7x plus 3. So 7 times x, but instead of x, I'm going to plug in my g function, which is x squared, 7x plus 3. So that was pretty straightforward. Now here's how you do domains for composite functions. And these are all going to be pretty easy, but other problems are going to be trickier. you have to check the domain of two different things and you sort of union them together. You always have to check the domain of what I call the inside function. Inside function is like G. Now in this case, the domain of G is just all real numbers, or you could say negative infinity to infinity. So for this first one, the domain of G is all real numbers. So that's the first one you check. And then you have to check the domain of your final answer. So you have to check both of those domains. You have to check the domain of your inside function and then the domain of your final answer. Now, both of those, the domains are going to be negative infinity to infinity, or you're going to be all real numbers. So just go down here. As a matter of fact, since neither of these have any fractions or square roots, I'm just telling you now, for all these composites, the domain is going to be all real numbers. So this one's, the domain's not too difficult. So the next one they want is G composite F. So once again, G composite F of X means G of F of X. So that means I go to my G function. Every place I have an X, I replace it with the whole F function. So the G function is just X squared, but instead of X, I put in the F function. So what I think they probably want you to do is to multiply this out or to FOIL it. If I do it in my head and not mess up, I think it's going to be, 49x squared plus 42x plus 9. And that's correct. And once again, the domain is all real numbers. Now the next one, F composite F. F composite F means F of F of X. So it's interesting, you go to your F function, every place you have an X, you replace it with the F function. So 7x, instead of X, I'm going to put the F function, which is 7x plus 3. So this is 7x plus 3. If I multiply out the parentheses to simplify, that's going to be 49x. 7 times 3 is 21 plus 3, 49x plus 24. And the last one, G composite G. G composite G is G of X. So you go to your G function. Every place you have an X, you replace it with the whole G function. So G of X equals X squared. Instead of X squared, I put in the G function, which is X squared. So really it's X squared, the whole thing squared. Should be X to the 4th. And of course, all these are, the domain is all real numbers. All right, so let's do this. Let me stop now and I'll start the new video, a new video with number 10.